Welcome everyone to this webinar from the Flexi-Sync project. So today it will be me, Johan Kensby, and Filippa Sandgren speaking. We are both from Utilifeed, and we will be speaking about this optimization tool that has been developed in the Flexi-Sync project and is now being tested by our demo sites. And before we get into the webinar, I just want to notify you that this is being recorded, but it's only the presentation part that is being recorded. Afterwards, we're going to have a session of questions, and that part we won't record. Also, if you have any questions, you can write them in the chat, or at the end of the presentation, you can raise your hand, and Anna Nilsson from IVL will hand out the word and keep an eye on the chat. So I think we'll just get started by introducing ourselves. So my name is Johan Kensby. I'm the CTO and co-founder of Utilifeed. And Utilifeed is it's a startup company from Göteborg, and you can just very shortly say that we help energy companies to become data-driven in basically everything they do across their whole value chain. Anything from automated validation of data to designing new price models to optimizing the design and operations of energy systems. That is what we're talking about today. And with me, I have my colleague Filippa.
Yes, hello everyone. My name is Filippa Sandgren, and I work together with Johan at Utilifeed. I'm a product owner for energy systems, the services regarding energy systems, and the optimization that we are developing is part of that. So I'm responsible for the development of the optimization tool.
Okay, so thank you, Filippa. Let's get started. I will start with a general introduction to what we're doing and why we're doing this, and then Filippa will have a demo where we dive deep into the tool and see what it is that has been built during this project. So I just want to start by highlighting why this is an important topic, and it's becoming more and more important as time goes. Like what you're seeing here, it's the electricity price from a day last month. This is from Nord Pool they had in SE3, which is mid-southern part of Sweden, but the European electricity market is very much connected, so the situation is similar in many other places. And you all seen big headlines this winter about the record high prices, but what hasn't been written that much about is how big the variation have actually been. The prices have not been high all the hours during all the days. And if we look at November and December, in this area in the electricity grid, it has on average been a factor 10 between the highest and the lowest spot price on the market during each day. So this is a huge variation. And in fact, all days, the factor has been at least 1.8 between the highest and the lowest price in any given day. So what does this mean? The one with the flexibility is the winner. So there's a huge value in shifting use of electricity in time to the points with the lowest prices, or shifting generation of electricity in time to the points with the hours with the highest prices. And this connects a lot to the district heating grid, which is very much interconnected with the electricity system. And jumping into and even more of a bigger picture on why we're doing this and why the situation looks like it does. So we have an energy system which is having an increased share of renewables that is often intermittent, and we also have a constant shifting demand of both the supply and demand in the whole energy system. And there are a lot of connections between district heat and electricity. The most obvious ones are that a lot of the district heat is produced by combined heat and power plant that produce electricity and heat at the same time. But there are also quite a few heat pumps in district heating grids, and in some grids still have electrical heating in them. But also there are more indirect connections. In Sweden, for example, it's fairly common, and it's becoming more and more common, that buildings have both district heat and a heat pump. So it's fairly common for residential buildings to have an exhaust air heat pump that covers the base demand and district heat to cover the peak. And these heat pumps are normally run like prioritizing the heat pump all the time and then peaking with district heat. But if we look at the last picture, we should really turn them off when the electricity prices are high and operate them more flexibly. And these are just some examples of flexibility, but there are also a lot of other types of flexibility in district heating grids. You have the grid itself, you have hot water storage tanks, for example, and demand flexibility. And this flexibility can be very, very cost effective. If you, for example, compare prices of hot water storage tanks to battery storage, which has fallen a lot in price the last decade, it's still 10 to 20 times cheaper to store thermal energy in a storage tank than to store electricity in a battery. Of course, I know that electricity is a more refined or a higher quality form of energy, but it still speaks something with this huge difference in price per storage capacity. And what all this means is that district energy system have a great opportunity to help stabilize the electricity grid and at the same time increase their bottom line, the revenue. So, and this is thanks to the big amount of sector coupling between the two systems and the availability of cost-efficient flexibility in district heating grids. But in order to do this, we need to overcome a number of challenges. When you connect these systems together and optimize them together, it becomes a fairly complex optimization problem with many variables to consider. You also need, really need to have the system perspective that widens the system boundary. Also, you need to collaborate between different partners, especially if demand flexibility is involved, because then you do some control in a building, which has an effect on the district heating grid, that also interact with the electricity grid. So you really need new business models for this that share the value that is created between the parties that are part of creating it. And that is exactly what we've been working on in this project, all of the challenges above. And what we will dive more into now is the tool that optimizes how you should operate an interconnected system. So what has been developed is a model-based optimization tool that can handle flexibility. And the reason we're running with this model-based optimization is that we are working with such complex and interconnected systems, so you can't really do this with a traditional control logic. Like when the decision on when you should run a heat pump, for example, isn't simply a threshold of the heat demand or at a certain electricity price. It depends on forecast of demand and price and how you can utilize flexibility to store it between different days. It also depends on ramp speed, start and stop costs of all other units, when it's worth turning them on and off, and so you can't really work with this traditional control logic. What you do instead, or what we have done, is created a tool where we can build digital twins that includes all production units in a district energy system, like boilers, heat pumps, combined heat and power plants, and so, including their connections to the electricity grid. All centralized flexibility, like the storage tanks. Also the demand flexibility in the buildings, For example, if you have a building heated by a radiator heating system, I can, for a couple of hours in a day, turn down the amount of heat I supply to the radiators, and it will have a minimal impact on the indoor climate, as long as I, during other hours the same day, supply a little bit of extra heat to balance it out. And this is because of the big thermal inertia in the building. And in this demand flexibility category also includes the buildings with both district heat and the heat pump, where you should really operate the control of these systems depending on what is on the margin at each point in time in the electricity grid and in the district heating grid to where the building is connected. We also, of course, model the distribution grid, because you also have a thermal inertia and time lag when you vary the temperatures in the supply pipes. So this is a type of flexibility you can utilize. And also a really good forecast of the demand in all buildings is part of this twin as well. So what do you do when you have built a twin that describes, it basically becomes a huge equation system describing all these components, not only for each time step, but how all the time steps are connected. You can then apply model-based optimization to this. And this is something that can be done with the use of very powerful solvers. So if we plan like 1 week ahead based on the forecast, how to operate every component at every point in time in order to have the lowest operational cost or the environmental impact for the whole period, it is a mathematical problem that can actually be solved. And by building this digital twin with a huge equation system and applying it to the best possible solvers out there, then it can actually be solved. And the result is a plan such as the ones you have to the right here, where we basically find how should we utilize all this flexibility in order to cut as much cost or environmental impact as possible. So enough about the theory. Let's jump into how the tool actually looks and what can be done with it.
Yes, so thank you for that introduction, Johan. Yes, so Johan already mentioned a lot of the key features that we have in the optimization. So, but I will shortly list them here. So first of all, we have the load forecast with our own machine learning algorithm, Energy Predict. And this is a tool where we use the actual consumption in the substations to predict the load instead of using the historical production. And this gives a more accurate load forecast than you just using the historical production. And I will give you a very short demo of how this load forecast works later on when we come into the demo. And we also use an electricity price forecast that we buy from an external source to use as an input in the optimization to also optimize the use of electricity in the district heating grid. And as Johan mentioned, flexibility is a part of the optimization, and that's one of the key features that we have. And especially in the Flexi-Sync project, we have the demand side flexibility from Noda that I also will describe a little bit more in detail. You can go to the next slide. So the user story for our production optimization is to plan the daily operation of the system and about 7 to 10 days ahead. And that's usually how long the weather forecast we have. So what the user does when they enter the optimization tool is first to do some input values. So to look at the availability of the units in the system and look at the fuel and electricity prices for the coming days and get the heat demand from Energy Predict. So what will the load actually be for the coming days? And also get the available flexibility from Noda in this case. So how much flexibility can be used from the buildings in the upcoming 48 hours, because that's how long the flexibility forecast is from Noda. And then the user performs the optimization and then gets some output. And the output is an hourly heat production plan. So how each unit in the system will be controlled during the coming days. And that includes the storage, like an accumulator tank, the demand flexibility from Noda, exchange with other grids, if that's possible, and also the hourly electricity generation and consumption plan. So how much electricity will be used or consumed during the coming days. And this plan can then be used to place your bids on the electricity market. And then when the user has looked at these outputs, they explore the results and make sensitivity analysis if it's needed. And when the user is happy with this plan, you can set the operational plan, and that means that the flexibility plan that was an output from the optimization. That flexibility plan can be sent back to Noda. And I will go into a little bit more detail about how that connection to Noda works. So if we look at this picture from left to right, so on the left side, we have the district heating utility. They are the only ones doing something manually here, let's say. So they are performing an optimization. And they are doing it by using the utility platform that I will soon show you. And the utility platform then speaks to Noda. And Noda has a lot of information about the buildings. So the buildings is to the right. So when an optimization is performed in the utility feed system by the district heating utility, then the utility feed system gets the available flexibility from the Noda system. And Noda uses the indoor temperature and the demand forecast and the thermal inertia data from these buildings to predict the forecast, the flexibility forecast for the coming hours. And this data is then sent to utility feed system and used in our optimization tool. And the outcome from that optimization tool is the actual flexibility plan. So how the flexibility should be used. And that control signal is sent back to Noda, and Noda then does the control of the buildings. And that can either be by a change in the indoor temperature, like increasing the heat delivery or decreasing the heat delivery for a couple of hours, or it can be by switching between heat pumps and district heating as a heat source in these buildings. So we have two different kinds of demand flexibility from Noda. Yeah, I think that was it for the presentation. So then I will go over and demo how it looks like in our platform and what we have developed the last year almost. So I hope you see my screen now, right?
Yes.
Yeah, good, perfect. Is it enough zoomed in? Can you see the values here? Since I'm on a very large screen. Or should I zoom in a little bit more?
I can see on a fairly small screen.
Yeah, okay. Then I think it's okay. Just let me know otherwise. So first of all, I just want to show you our load forecast tool. So here we use Energy Predict to actually predict both the energy and the volume flow and the return temperature in the substations in the system. And here I can show you both predicted values and observed values, since we're looking at an historical period. We're looking at February 2019 here. So the black lines is the observed energy, and the thick purple line here is the predicted energy. And then we also have an interval where we show the upper and lower values. Like, yeah, it's most probable that it will be between the upper and lower lines. But as you can see, the model predicts pretty much pretty accurate so the model and the observed values are almost the same. So we can see here that the model performs well on this during this period, and we can see it both on the energy and the volume and the return temperature. And these values here for the energy is what we have used for the load forecast in the optimization tool. So this was something that we had before Flexi-Sync started, but we have used it as an input to the optimization. And if we instead look at the optimization, we can go in here. So the optimization tool that we have built consists of 3 different tabs here. So we have the operational plan, which is the actual plan that the utility company has decided that this is how we should run our system the coming days. We have the simulation results, which we will look at soon, where you do your simulations to get your results. But you always start in the configuration builder. Here is where you make the settings of your system. First, we can look at the default settings. So here in the default settings, you have a list of all the components in your system. And this is our testing network. And we have chosen that our testing network should consist of both heating and cooling. So the optimization can do a combined optimization with a connected heating and cooling system. So we have a lot of different components here. We have absorption chillers, combined heat and power plants. We have cooling storage, external connection, heat-only boilers, heat storage, and so on. So if we go in and look at one of these components, this is an heat-only boiler running on biomass. We can see the parameters of this boiler. So we can see what the maximum heat output is. That's 20 megawatt. We see the ramp up speed and ramp down speed, and we see the minimum heat output. The thermal efficiency is set to 91%. We have a fuel cost and also starting cost for this boiler. And in the same way, we can go and look in, for example, the combined heat and power plant, which has a lot of more parameters since it's a more complex component. So here we have 4 different operating points. So we have an operating region for the CHP plant. So this point here is for when we're producing maximum of electricity, maximum of heat, and what the efficiency is at that point. And then we have corresponding points for min electricity and min heat output. And also here we can state an electricity price, a fuel price, and a starting cost. And we can also look at the storage tank, for example. Here we have some losses. We have some maximum heat input and output. We have a maximum storage capacity and also minimum values for these. And for this one, there are no economical parameters, so there's no fuel or electricity used. So this is the default settings for our system. And now when I'm doing this demo for you, I want to do a simulation without the cooling components, since that's easier to show you. So I've created a known configuration that's called without cooling. And for that configuration, I can go in here and do some deviation settings. So I start with going into the absorption chiller, for example, and then I disable the component because I don't want it in this configuration. So I set the dates for the disabled, and then I click save. And that I have done for all cooling components. But we can also, for example, go in here to the storage tank and make a new event. And then we can set the, for example, we can change the maximum, or we can change the minimum storage capacity, which is here. So now the minimum storage capacity is 50 megawatt hours, but maybe we can change it to 40 megawatt hours instead. And then we can say here, lower min value. And then we need to set a date. So we take the whole week and we can save it. And if you go in here then on technical parameters, you see that we have changed the values for the minimum storage capacity. And when we are happy with our deviations that we have made, you can go into simulation results. So here's where we actually do the simulations. So now I choose the same configuration, this one that's called without cooling. And what I need to do now is that I need to enter start states for all of these components. So when you do this in a real system, you usually go in and look at how are these plants running right now, and you enter these values. But since this is a made-up system, I need to input good made-up values here. And since I've done this before, I hope I know what I should enter. And then I want to set the dates for my simulation. And I start with today and 3 days ahead. And I click run simulation. And we just hope that we get a good result. Yes. So here we got some results. So first, we get some KPI values. And then we also have our heat production plan. So we start by looking at the KPI values. We see the total production costs for this period. This period is about 3 days. We see the revenue for the sold electricity. We see the net cost per unit of heat. And we see the total heat generation, the electricity generation, and the electricity use, which is 0 since we don't use any electricity in this particular simulation. So if we look at the heat production plan, we can see that this orange line here, that's the demand. And that we got from the same model as this one. So that's from Energy Predict. And then we can see how the model chooses to run the different power plants or heat plants. So we see that the CHP is running here on maximum capacity all the time. We have the heat-only boiler on biomass running. And then we also have the CHP running on bypass sometimes. And we can also compare this to the weather. So we see this is the solar radiation. We see the outdoor temperature, which is pretty stable between 0 and 4 degrees. And then we have the wind speed. And if we look at the electricity prices that we see here, so this orange line is the electricity price, and the green is the electricity produced by the CHP plant. So what we can see here, that when we have lower electricity prices, we do not produce any electricity with the CHP. And if we go up here again, we see that the CHP is running on bypass mode. So it's actually not producing as much electricity as it could. And that is because of the lower electricity prices. And we can also see how the marginal production cost of heat is during this period. I'm sorry for that. So with this simulation here, it's pretty stable. It's just a bit higher in the beginning. And what we also can see here is that when the demand and the supply doesn't match exactly, that means that we're using the storage tank. So in this period here, we're charging the storage tank and then we discharge it. And here again, we charge it and here we discharge it. So we're using the flexibility in the storage tank almost all the time here. And if we would have, if I should have showed this on one of the demo networks in Flexi-Sync, I also could have showed you how the NODA flexibility works. But right now we don't have any test grid for the NODA connection, so I can't really show you that since I'm showing our test network right now. But what you do is you click this box here, fetch flexibility, and before you run your simulation, and that means that the flexibility is fetched from the NODA system, and you will see it also as a flexibility here, and also in flexibility graph down here, which is now empty. So yeah, that's how it is. Johan, do you have anything to add here during the demo or something I've missed?
You just added that. Maybe I can just give a little bit context like of the deviation settings that we were doing. So for example, for the storage tank, if you storage tank is not only used for flexibility, it's also used as a backup security of supply. So that is kind of the use case why you would want to set. So the optimization never plans for the storage tank to drop below 40 megawatt hours. Because if you have a failure in the system, then you have that as a backup. And during certain periods, you might need more backup, and during other periods, you might need less, and the optimization will handle that. So.
Yeah, and another use case for the deviation settings is of course if like one of your components is out of operation, for example, it might need service or anything, and it can also be the other way around, that you're actually doing a test on one of your components, so you want to force it to be on during a day or so. So there can be many different reasons for why you would like to do deviation settings. And if you, for example, have one component out of operation for some reason, then you maybe want to lower this security that you have in your storage tank because you want to use it more, for example. So that's why that is something that you need to do like each time or every day that you're using the optimization tool.
Yeah. Great.
Yeah, but that was everything that I planned to demo. So I guess we're opening up for questions, or you want?
I just wrap it. I'm just gonna wrap it up.
Yeah.
Before, yeah. So right now, 3 grids are. There's 3 grids in Flexi-Sync who are testing this right now, and we're soon we'll start testing all the remaining grids. And before we go to questions, I just want to reach out and say that this is a part of a webinar series, and the next webinar will be held in April or May. Topic is not yet set, but if you want to be alerted on this webinar, like sign up for the newsletter or look in every now and then on our web page or LinkedIn.